Good afternoon, everyone. Today I will be talking about the allotropes of carbon. What are allotropes of carbon? It's a substance containing a large number of atoms which are covalently bonded, which gives a giant molecular or giant covalent lattice. There are three examples of molecules made from nonmetals which are giant structures. These are graphite, diamond, and Buckminster fullerene.
The first allotropes of carbon I'm going to talk about is graphite. A graphite is gray in color and it has a crystalline shape or form. Its structure consists of hexagonal layers of interlinked carbon atoms, which are known as graphene, held together by weak intermolecular forces, which is van der Waals forces. Graphite was first discovered in Cumbria in North England at the beginning of the 16th century. Although it resembled coal, it would not burn. It did, however, prove to be an excellent marker of ships' skins. Uses of graphite: writing materials, lubricants, refractory, nuclear reactors, batteries, or graphene sheets. So the particles in a graphite molecule is carbon atoms. The forces between them is covalent bonds by van der Waals forces between the layers. Graphite has a giant molecular structure and arranged hexagonally. The coordinate number of carbon is 3, which means that one carbon atom is covalently bonded to 3 other carbon atoms. There are 3 main properties of graphite. Number 1 is that it has a high melting and boiling point because of the large amount of energy needed to break the strong covalent bonds between the layers. Second is that it has a good conductor of electricity. Due to the delocalization of electrons in the plane of layers, electrons can move along the layers but cannot move freely between the layers. Number 3 is that it has a slippery and lubricating properties because of the weak van der Waals forces between the layers, and the layers can slide over one another. The second allotropes of carbon I'm going to talk about is diamond. Diamond is a solid form of the element carbon with its atom arranged in a crystal structure. The lattice particles in a diamond molecule is carbon atoms, and the lattice forces of diamond is strong covalent bonds. The structure of diamond. Diamond has a giant molecular structure. It consists of 3D hexagons with each carbon atom being joined by strong covalent bonds to 4 other carbon atoms in a tetrahedral arrangement. The coordinate number of carbon is 4, which means that one carbon atom of diamond is covalently bonded to 4 other carbon atoms. There are 3 main properties of diamond. Number 1 is that it has a high melting point of 4500 Celsius. Because of a large amount of energy is needed to break the strong covalent bonds. Number 2 is that it is a non-conductor of heat and electricity, because there are no free-moving electrons to carry the current, as all valence electrons are involved in a covalent bond. Number 3, it is very hard. The structure is very hard and rigid due to the strong carbon-carbon bonds and the tetrahedral arrangement of atoms, a 3D network of interlocking hexagons, preventing the atoms from translational motion. The last allotropes of carbon I'm going to talk about is Buckminster fullerene. Buckminster fullerene is an allotrope of carbon with a molecular formula of C60. However, it is only a simple molecular formula. The molecule itself is held together by covalent bond between carbon atom, but in a substance is held by weak intermolecular force known as van der Waals force. The molecule itself is held together by covalent bond between carbon atom, but in a substance is held by weak intermolecular force known as van der Waals forces. Because of this, it will have a lower melting point than the other allotropes of carbon. The carbon atoms of Buckminster fullerene are arranged in pentagons and hexagons, resulting in a hollow cage. The carbon atoms of Buckminster fluorine are arranged in pentagons and hexagons, resulting in a hollow cage that shares a resemblance to a soccer ball, which mainly gives its nicknames buckyballs. So the uses of Buckminster fluorine. The uses of Buckminster fluorine are drug delivery systems, lubricants, catalysts, treat cartilage degeneration, and bone destruction. There are three main properties of Buckminster fluorine. Number one is that the substance has a low boiling point and melting point, because low amount of heat energy is required to break the intermolecular force between the molecules. Number two is it is a simple molecular solids and it can conduct electricity due to the presence of mobile electrons as a result of unpaired carbon electrons. Number three, it is soft. It requires small amount of work to break or cut a substance of Buckminster fluorine. Thank you for giving your time to watch my presentation on allotropes of carbon. Please like and subscribe to the channel.